Hey everybody, and welcome back to The Explainer. Look, I know we're right in the thick of finals week right now, and your stress levels are probably completely off the charts. But hey, take a deep breath. Today, I'm going to be your virtual peer tutor. We are going to completely lock down the equilibrium of coplanar non-concurrent force systems. Think of this explainer as your ultimate final revision session. We're going to strip away all the textbook fluff, focus purely on the core mechanics of support reactions, and get you fully prepped to absolutely crush those exam questions. So here is our ultimate revision roadmap for today. 1. Decoding support types. 2. Identifying beams. 3. Calculating loads. 4. Common exam mistakes. And 5. The problem-solving playbook. Let's get right into it. Section 1. Decoding support types, the foundation. Okay, mastering how structural supports react is the absolute foundation of everything else you'll do on this test. If you misidentify a support, your free body diagram is going to be wrong from the jump, and your final answers won't stand a chance. So think of simple and roller supports as your first mental flashcards. A simple or roller support exerts a reaction strictly perpendicular to the plane of the support. Basically, they restrict translation, like sliding movement, in just one single direction. And here's the absolutely crucial part for your diagrams. They do not restrict rotation at all. The beam is perfectly free to pivot around that point. You can really see the visual contrast between reaction forces here. On one side, a beam resting on roller supports simply pushes straight up. But contrast that with a hinged or pinged support. Notice how we have to resolve a hinged reaction into two distinct components, an X and a Y. Why? Because hinged supports restrict translation in both horizontal and vertical directions. It's locked in place. However, just like the roller, it can still spin. Rotation is totally allowed. And then we have our final and honestly most rigid support type, the fixed support. Guys, this is the ultimate anchor. A fixed support restricts literally everything. It restricts translation in both directions, locking it down horizontally and vertically so it can't slide. But crucially, it also prevents the body from rotating by developing an internal moment, which we call a restraint moment. That restraint moment is actively fighting against the beam's urge to bend or rotate at the wall. Honestly, I highly recommend taking a quick screenshot of this matrix right now. This is your ultimate cheat code. When you sit down in that exam hall and start drawing out your free body diagrams, just refer back to this mental table. Simple and roller supports? That's one force vector. Hinged? That's two force vectors. Fixed? Two force vectors plus a restraint moment. If you memorize this simple matrix, I promise your free body diagrams will practically draw themselves. Section 2. Identifying beam configurations. Now that we actually know how supports behave, let's quickly test your ability to visually classify the beams that sit on top of them. Here are your next visual flashcards. On one side, we've got a continuous beam. It's super easy to spot. You'll know it's continuous if you count 3 or more supports sitting straight underneath it. On the other side is a cantilever beam. This one is entirely fixed at one end, locked into a wall and completely free, just dangling out in space at the other end. Now compare those to these two tricky variations that examiners absolutely love to throw on tests. First is a propped cantilever beam. It looks exactly like a standard cantilever that's fixed at one end, but there's a sneaky added simple support propping up the free end. Then you have an overhanging beam. See how the simple supports sit at the base, but the actual physical beam extends way past the last support? That extra floating portion is your overhang. Identifying these instantly is going to save you so much precious exam time. Section 3. Calculating complex loads. All right, time for the heavy lifting. The trickiest part of this exam usually isn't the supports. It's identifying and calculating the complex loads acting on the beam. I mean, concentrated point loads are easy points, right? But what happens when the load is spread out? Enter the uniformly distributed load, or UDL. This is a load that's spread evenly over a certain length of the beam. The absolute golden rule here, the thing you must remember, is that you cannot easily solve equilibrium equations with a distributed load. You first have to convert that entire distributed weight into a single, equivalent point load acting directly at the center of that particular span. So, how do we actually handle this when the clock is ticking? It's really straightforward. Let's say you need to resolve a UDL of 20 kilonewtons per meter acting over a 3-meter span. All you do is multiply the magnitude by the span distance. So 20 kilonewtons per meter times 3 meters gives us a total magnitude of 60 kilonewtons. Boom. Then we just drop that new 60 kilonewton point load dead center into that 3-meter span. Section 4. Common exam mistakes and pitfalls. So the crucial takeaway here is avoiding the massive trap that most students fall into when the exam inevitably throws a curveball. And that curveball happens when loads stop being nicely uniform rectangles and start varying in shape. When you see a triangular load, which is called a uniformly varying load, alarm bells should be ringing in your head. The most common pitfall, the one that will instantly tank your grade on a 20-point question, is treating a triangle like a UDL and just slapping the equivalent point load right in the middle of the span. No way. You absolutely cannot do that. This quote right here, massive red flag to watch out for. Burn this into your memory right now. The point load acts at the center of gravity of the triangle. If you miss this detail, your moment arm distance will be completely wrong, which is like a domino effect that ruins every single equilibrium equation you write afterwards. So, here's your formula flashcard to solve this without breaking a sweat. First, you find the magnitude by simply calculating the area of the triangle. Just 1/2 the base times the height. For instance, if you have a 2-meter base and a height of 2 kilonewtons per meter, you multiply 1/2 times 2 times 2, resulting in a clean 2 kilonewton point load. Then, the secret sauce. You place that force exactly at the center of gravity, which, for a triangle, is always exactly 1/3 of the way from the heaviest, tallest side. Section 5. The Problem-Solving Playbook. Okay, we've covered supports, beams, and tricky loads. Now, let's bring all these puzzle pieces together. I want to leave you with a foolproof, step-by-step checklist to solve literally any coplanar non-concurrent force problem they hand you on test day. Follow this simple 3-step playbook. Step 1. Recognize your 3 conditions of equilibrium right out of the gate. Sum of forces in x equals 0, sum of forces in y equals 0, and the sum of moments equals 0. Step 2. Look at the beam and convert all those tricky, uniformly distributed and varying loads into simple, easy-to-manage point loads. Step 3 is your actual free body diagram guide. Just visually isolate the beam, replace every physical support with the correct reaction arrows from our cheat code matrix, drop in your converted point loads, and finally, do the math to solve for those missing reactions. And that brings us to the very end of our revision session. So I'm going to leave you with this final challenge. When you look at your practice problems tonight, ask yourself, have you truly mastered how to turn a complex, scary-looking loaded beam into a clean, simple system of point loads and reactions? Take one last look at your notes, definitely review that support matrix, and remember to watch out for those sneaky triangular loads. You have absolutely all the tools you need to crush this. Good luck on your final exam and keep learning.